So let's go. I could have done that prettier, but sorry. So let's talk about dipoles again. Just a little review. What is a dipole? Positive and negative charge stuck together. We went through this whole thing, right? You have this positive and negative charge stuck together. There's all this stuff. There's the electric dipole moment, which points from negative to positive. And of course, if you put a dipole in a field, right, it rotates because torque. All right, and we went through all of this, but it'll end up lined up like this. And if you call this a dipole, it lines up like this. Oops.
Do we need that?
I don't know what happened here. There we go. Torque. Yeah, yes, torque, right? So this is dipole moment crossed with the electric field, which tells you that if you're not lined up with the electric field, it's going to create a torque to try to line you up with the electric field, okay? And then potential energy is just negative dipole moment as a dot product of E. Okay, remember guys, we talked about this like long ago when we talked about charge, but this is a review, okay? So this is our minimum potential energy. That's where it's lined up with the field. Our maximum potential energy is where it's anti-parallel to the field, okay? And this is 0, which is only significant because of the dot product, but it just is in the middle, okay? But insulators are generally made of dipoles, all right? If you bring a charge close to a dipole, it'll behave in these ways, all right? So let's talk about what happens when you put insulators in an electric field, all right? So let's say we put this little thing. This is an insulator, so it's made up of a bunch of dipoles. Let's say we put it in an electric field, just a bigger electric field that comes from outside. Okay, so let's say you place it in, like, I don't know, what would create this kind of electric field? A capacitor. It's a nice, constant, uniform electric field. It's from a capacitor. What's going to happen to these little dipole guys? Yeah, they're going to rotate to line up with the electric field. Okay? Well, that means more positive charge points this way and more negative charge points this way. And each of these things has a little electric field that points from positive to negative. Okay? So if each of these things has a little guy that points from positive to negative, that means there's an electric field that points this way. Well, what do we know about electric fields at a point? Can you add them up? Yes. Okay, so if you have an electric field going this way and an electric field going that way, remember for a conductor, they exactly canceled. But for an insulator, it just makes the net electric field in here a little bit smaller. Okay, so let's look at that again. So let's say we have a capacitor. Here's the field for the capacitor. All right, we throw our insulator in here. Here's the fields for each of the little dipoles. Okay, what happens to the net electric field? Does it go away?
No, it just
gets smaller. Okay, so the net electric field gets smaller. So the electric field inside your capacitor goes down. Why would that be useful?
To regulate?
Regulate what?
Energy?
It's one possible thing, right? How are actual capacitors made usually? Depends on the material, right? We've been talking about, well, when we calculate the capacitance, we have to include the material between the plates. Guess what the material is?
Like an insulator?
Yeah, an insulator, right? There's two reasons the insulator's good. One, if you put two metal plates together and you roll, if you put foil together and you roll it, is that a capacitor? No, because if the plates touch, that's no good, right? So you want something that separates the plates that's not a conductor. Well, there's only one other option. You have to put an insulator between them, okay? So there's just a logistical reason why we want to do that. But there's an extra benefit because what you want to store more energy in a capacitor is what? More charge on the plates, right? You want to store more energy, you need more charge. You want a bigger electric field, you need more charge, right? The only thing that changes the electric field really is charge on the plates. Is there a limit to how much charge you can store on the plates?
Yes.
Probably, right? There's probably a space limit, and there's also something else that happens, okay? But we're going to get to that. So insulators in a capacitor, we have a special name for them. They're called dielectrics, okay? All dielectrics mean is insulators in a capacitor. So if you have a capacitor and you put paper in between the plates, that's an insulator, okay? If you have a capacitor, you put plastic in between the plates, that's an insulator, okay? You put glass in between the plates, that's an insulator. So because of the induced polarization, the field in the dielectric is smaller than it would be if you didn't have it there, if there was just a vacuum, all right? And we have something called the dielectric constant K, or well, kappa. That's the Greek K. Just like, I don't know. To join a fraternity, you can learn the Greek alphabet.
You do. It sucks ass.
Do you know the Greek alphabet though?
Last year, yeah. I had to learn it from materials.
You already forgot it?
Yeah.
Well, anyway, there it is. Kappa is somewhere.
Fourth row, second
Here we
window.
go. That's kappa. Okay, so this is a lowercase Greek K, kappa.
Okay. So we have been working with.
Not, yeah. So we, come on, context clues. K, kappa. You have to, I know. Okay. Be careful with how you write things. Okay. This is physics slash penmanship. All right.
Physics / calligraphy.
Yeah. Good luck. All right. The good news is if you do things on a computer, it does have all of these letters for you, but it's not going to necessarily help you do your homework, but it will help you enter the answers into Pearson. So Pearson can tell the difference between K and kappa, unfortunately. So the new electric field is whatever the original electric field is divided by kappa. Now, if this needs to be smaller, what sort of values would you expect kappa to have? Bigger than what? Bigger than 1. It has to be 1 or bigger, right? If kappa's 1, that's a vacuum. Okay? So that means these are equal. If kappa's 2, right, then this value is going to be smaller than this value. So like let's say this is 10. If kappa's 1, these are both 10. If kappa's 2, what's this now? 5. Okay, so it gets smaller. All right? Okay, so we scale down the electric field by a kappa. These are all different looking capacitors. They're cute. All right? Except for there's some giant ones. Have you ever seen the capacitors in like an AC unit? They're gigantic. Like I think I have one in my office. It's like this
Oh,
big.
you're talking about the blocks?
It looks like a little tiny canteen, you know. So, yeah, they're crazy.
Stick your finger and touch it.
Just make sure it's discharged first. And that's why you want to make sure not just to unplug the power, but see if the capacitors are discharged before you work on large electrical systems. Okay, so for a parallel plate capacitor, this is the capacitance. And we talked about how this might have something to do with the material, and currently it's a vacuum, okay? So how can we maximize capacitance? How can we make it bigger? What things can we do? How can we make this bigger?
Reduce distance.
You can reduce the distance.
Or increase the area.
You can increase the area. You can change the material. Okay, so you can make the area bigger. Here, I animated it for you. Look, it's bigger now.
Wow.
You can decrease the distance. Did I do that? Yeah. Look. But how how small can you make this distance? What's the limit?
As long as it doesn't touch, right?
Because, like, think about it, okay? If you're charged and the doorknob is neutral, right? Let's say you have a little bit of electric charge because you have, I don't know, long hair, it's a dry day, or you're shuffling your feet on the carpet. How close do you get before it shocks you?
What distance do you?
But, like, is it a big distance or a small distance?
Small distance.
Small distance. Do you think it would be the same distance if you had more charge?
No.
No. So there's some limit, right? And what happens when you actually get shocked, Is it when you touch it or right before you touch it?
Before you touch it.
Right before you touch it. So what's happening there? What's happening with the electrons? They're jumping. Okay? There's a name for that. It's called Dielectric Breakdown. Here, there. That's my dramatic slide. Dielectric Breakdown. I should have had like the thunder sound. That would be really exciting. Just like, yeah, I have to like program the lights to flicker in the room. So here's a chart of various dielectric strengths. Yes.
Should we write that down?
What?
The chart of dielectric strength.
Do you want to write down this chart?
It was a question.
No, don't write down charts.
Alright, because I saw a lot of pencils hit paper right now, and I'm just wondering.
No, this kind of stuff. If you have a problem like that includes this, I'll give you this information because this is not something you need to necessarily know off the top of your head. It's not like the charge of an electron, which you should know.
What is impregnated paper? Paraffin impregnated paper.
It's when a candle and a paper have a baby. No, it's just wax paper. Engineers are gross.
I don't understand why it's called impregnated paper. It's a weird way to phrase it.
Okay. So the dielectric strength, this is the maximum electric field that you can have between two objects before you have dielectric breakdown. Okay? So in terms of our like electric shock thing that we're doing, right? If we have a static shock, that means the electric field of like 3 electrons on your finger versus that. As you get closer, right, what happens to the electric field? Gets stronger, right? So as you get closer, the electric field gets stronger, and therefore, okay, when you reach this maximum electric field, that's where you get dielectric breakdown. All right? So at a particular distance, you'll get dielectric breakdown for any particular electric field. But the electric field is the limiting factor. Okay? So when you reach this electric field, that's when you get dielectric breakdown. That's also how lightning happens, okay? Yes?
So when you get to the breakdown, is it like the overload point? Because the electrons are jumping?
Yeah, dielectric breakdown is the point at which electrons will jump across a space.
Is that yeah, but that's like the overload. That's like.
Well, I don't know what you mean by overload.
Like, you can't get any closer than that point because the electrons are jumping.
It means as soon as you reach this electric field, electrons will jump no matter what the distance, no matter what else is going on, right? That's when if you have a bigger field than that, then it's just easier for them to jump, right? But if you have a smaller field than that, then they're stuck on their individual things. Yeah. So here's so for various materials, here's the dielectric constant kappa. Okay, because remember we said for a vacuum, what should kappa be? 1. For a vacuum, kappa is 1. Okay. Air is pretty close to a vacuum, right? It's 1 to the 4th decimal place. Okay. Let's find some. Let's see. Neoprene rubber, 6.7. Okay. What's the electric field strength here? 7 times 10 to the 6th. Okay, that's pretty big.
That's a lot.
Right? That is 10 to the 6 is what metric prefix? Mega, yeah. So 7 megavolts per meter. All right, that's a pretty big electric field. And let's say even paper, right? Paper has a dielectric constant of 3.7. You need 16 megavolts per meter to get dielectric breakdown. Okay, that's a lot bigger than 3. Okay, so if you're building a capacitor and you don't want the electrons to sort of arc to the other plate, just putting paper in between your two plates is more effective than air. Okay? Let's see, what's a good one? Teflon. Wake up. Teflon is a pretty good insulator. It has a dielectric constant of about 2. You need 60 megavolts per meter to do that. Vacuum is 1. Apparently doesn't have a dielectric strength. Things can just jump across the vacuum. Water, doesn't really count. Why does water not count? It's not a great dielectric because it conducts electricity, so it could just get across, okay? So any conductors, this doesn't need to exist, right? There's not like a limit. It can just travel across no matter what, okay? So this is only for insulators, and this is the electric field you reach before things start to jump, okay? All right, so, and in a capacitor, that's if it's a parallel plate capacitor, remember the electric field doesn't really depend on the distance. It only depends on the charge on the plates. Why does it depend on distance here?
That's not a plate, and you're not a plate.
I'm not a plate. What would be the charge? What would it look like? Point charge. And does a point charge depend on distance for electric fields?
Yes.
KQ over R squared. Okay, so as I get closer, the electric field gets much bigger. As I get farther away, the electric field gets much smaller. Okay. All right. So, how can we maximize capacitance? Well, we can make the plates bigger. We can make the distance smaller to a point. But the last thing we can do is we can add a dielectric in between the plates. Okay? And that's actually the most effective way because, as you can see, the dielectric constant scales things quite a bit. You can get a factor of 3 or 4 just from adding a dielectric into your capacitor. Okay? And that's 3 or 4 times the charge, 3 or 4 times the energy. All right? So here's our new formula. And I just want you to notice, so where should kappa go? Every time you see an epsilon naught, right? And these have shown up everywhere, okay? Whenever you see an epsilon naught, you can write it as kappa epsilon naught, all right? And sometimes we just write that as epsilon. But what that means is this is still 8.85 times 10 to the negative 12. We've been dealing with a vacuum, so we multiply it by 1, okay? If it's something else, you multiply it by that dielectric constant. So back to this chart, right? Oh, sorry, dramatic. All right. So if you have Mylar, you just multiply it by 3.2. And so this affects all of the things we did that involve epsilon naught, but primarily capacitors, okay? So that's just what I want you to think of. Because otherwise, it gets really confusing where you put kappa. The place you put kappa is always next to epsilon naught, okay? So this makes capacitance bigger, right? The bigger the kappa, the bigger the capacitance without changing anything else, all right? So that means we can write epsilon naught, we can switch it out with something we just call epsilon, right? Because epsilon naught is for a vacuum, so that's for a kappa of 1. But epsilon is just epsilon naught times your dielectric constant, okay? So this is where we swap out epsilon naught for epsilon, which depends on the material. And you can figure out what material it is and multiply kappa times epsilon naught, okay? And this, what was epsilon naught called? What's the name of epsilon naught? Permittivity of free space. Guess what epsilon's called? Just permittivity, right? Because free space just meant permittivity of a vacuum, and this is just called permittivity, okay? Or you could call it electric permittivity, but we have enough things that say electric in front of them, so we'll just skip it.
Why are you making this confusing as possible? Why not just add that on?
Calm down. Go do some yoga or something. All right. Okay, so here's a really old capacitor. This is not generally what they look like, but this still works. So let's try it out. you even touch them? It depends on what the charge is on the plates and how close your hand is to the plates.
Will it jump through, or will the electric field just pass through?
You say you'll
probably
die. Fuck.
But it vaporize.
No.
You'll pay for the thing. Just your hand dusts.
All right. It either increases, decreases, or stays the same. So please discuss. And we'll vote again.
What stays the same?
Get a bigger number and talk about this.
Can you guys fight to
The
this?
6 and the 9 look, I believe,
He thought you would hear.
Which
we should worry that he's been getting credit for. Oh, okay. Mystery solved. So it gets decreases, okay? Remember, how does electric field scale? It's the original electric field divided by kappa. Kappa is 1 or bigger, so that means it's going to have to decrease, okay? So what do actual capacitors look like? These are modern. That was a sort of historical capacitor. This is a modern capacitor, right? So there's various ways of making capacitors depending on how big of a capacitance you're going to need. The most simple ones, the ones we usually use in these sorts of labs, look something like this, right? So this is actually a pretty big one. But you basically take foil, you solder some wires to the foil, you put paper between the foil, you roll it into like it looks like a delicious roll of cake, okay? And sorry, I didn't eat breakfast. And then you put it into this tube and you can attach it to your circuit. Now, the ones we use are often really, really small, so they kind of look like they're like little rolled up foil, and then you dip them in plastic and they look like kind of like candy, but don't eat them, okay? And if you have really big capacitors, then you have things like this. So here's a metallic foil, like it's coiled just like over here, but you have some sort of, it's got some oxide layer, you have some sort of electrolyte inside it. Or you can have this in oil, like you can have these solid plates in a canister with oil. And the big capacitors look like this, which if you break some of them open, you'll have oil stains all over your stuff. Okay, so also you probably shouldn't just break capacitors open unless you're sure they're discharged, unless you like being electrocuted. Okay, but yeah, so this is this top one is a tubular capacitor, right? The round one that goes in the tube. Yeah. It's separated by paper rolled into a cylinder. This is a high voltage capacitor, so you can see there's many parallel plates separated by an oil, okay? And this is an electrolytic capacitor. All right, and there's other kinds too, but these are kind of the main ones you'll run into if you're dealing with capacitors. Anybody deal with big capacitors? What kind do you use?
The one with the oil in it.
Oh, okay.
We
Yeah.
had to discharge them, and then we had to keep them grounded out because apparently they charge in the atmosphere.
Yeah.
So,
Yeah, they can just charge up, and they're good at storing charge. So once they start charging, they just keep charging, and then it's just been sitting there, and you can touch it and die. So it's fun. Okay. Oh wait, so modern capacitors usually have a kappa of about 100. Okay, if you're using really big capacitors, like this should give you a kappa of about 100. Okay. So a lot of the stuff we looked at there was like less than 10. So you have to be more creative with the materials you use. All right. So anyway, here's our capacitor. Here's a dielectric. Okay. Definitions. A dielectric is a non-conducting material. What's another word for that? Insulator. Which, when inserted in a capacitor, increases the capacitance. The dielectric constant K is a dimensionless factor that indicates the capacitance increase when a dielectric completely fills the space between the plates. So if a dielectric doesn't completely fill the space within the plates, then you have to do the calculation a little bit differently.
So if you have this going on, and this thing discharges, it's discharging straight through whatever that medium is?
No, so usually when you're discharging a capacitor, you're connecting a wire from here to here. And if you're touching it, then it's discharging through you. Okay, so that's why you don't want to touch them, because it's really hard for the charge to go this way, so it goes any other way. So if you put a wire across the plates, or if you put your hand on both plates, that's when you're going to have a problem like that. The other thing is, I mean, even if you don't touch both terminals, right, if you're grounded and you touch the plate that's one of the plates that's charged, whether it's the positive or negative plate, it's still going to pass through you. So you just don't want to touch big capacitors if you're grounded. I mean, why do you think electricians wear those big rubber shoes, right? They want to be electrically isolated from the ground so that if they touch something, they're not automatically electrocuted. Yeah. Okay. So here's a little experiment we're going to do virtually. All right. So here's our capacitor. It's got some charge Q naught. Okay. So here's our voltage. All right, so we're measuring voltage. This is a little voltmeter. So it has a voltage V naught, and it has a capacitance C naught, which depends on the epsilon naught and the area and the distance. Okay, so all of that stuff, because it's a parallel plate capacitor. Here's the same capacitor over here, but we're now going to put a dielectric in it. Okay, what changes? Oops, no, sorry. No.
We know now.
Well, the electric field. What happens to the voltage?
It goes down.
Okay, it goes down. By how much? Kappa, right? It goes down by a factor of kappa, okay? So our change in voltage is our original voltage difference divided by kappa. So in this case, it went down by about half. What do you think kappa is? 2. Okay? How much does the capacitance go up?
It doubles.
If it's 2, yes, it doubles, right? So it goes up by a factor of kappa. Okay? And this is because, right, if you increase kappa, we have this equation, the definition of capacitance, okay? One of these things has to change if this goes up by kappa, right? I'm sorry, by not kappa. If this goes up by kappa, that means this either has to be 1 over kappa times delta V or kappa times Q, all right? Because these plates are isolated, what can't change? Q, okay? Charge can't change, that means voltage has to change. What if this was connected to a battery? Then what would change? The Q, right? If you're connected to a battery, the voltage is fixed by the battery. That means the charge has to change. And how much would the charge change? By kappa. Would you multiply it or divide it? Would it go up or down? Multiply it, right? The charge would go up by a factor of kappa, because in order to maintain the same voltage and have a larger capacitance, you can store more charge. Okay? All right. not sure. Please discuss.
Dielectric increase the capacitance.
So I was thinking of like potential. I was thinking of.
Can I write that down? It increases capacitance, so that means it has to, and it just said delta V. Delta V is equal to delta V naught. So if K is anything greater than 1,
It's sliding in and
it has to be enough. That's also the only way capacitance can go. That's it. Am I wrong?
What?
Yeah, but the volt stays the same.
I'm so tired. I was in a good mood for this. Okay, I'm gonna go fucking day again. Oh, shit.
All right.
Slid it in there.
One more. Slightly different answers. Better. So, what determines? So, okay. What does the dielectric do?
Increases capacitance.
Increases the capacitance. What does the battery do?
Maintain the voltage.
Maintains the voltage. So what should happen to the voltage?
Stays
Should stay the same because there's a battery that can change the charge connected to it. Remember, capacitance, when a capacitor is hooked up to a battery, the capacitor's voltage is determined by the battery. Okay? The battery has the power to add or subtract charge from the plates because this means that the plates are actually connected to something that allows charge to move. If there's no battery, what stays the same? Charge. Okay? All right, so it stays, in this case, the voltage stays the same. The potential stays the same. Okay? Here's another one. Okay? Discuss.
So if the capacitance and the voltage stays the same,
Everything is still the same.
I know, right? I figure it's just easier for me to be like, oh, now I know what I meant. Because if it's all in pencil or all in black ink, it's just like, what the fuck am I drawing?
What is this K?
What the fuck am I drawing?
Which K is this K? Yeah, well, that's the way I draw it. I was like that.
Why did you guys put
Because if it's the
But
battery,
like, for me, that's easy to remember.
So you know how the scientists that like discovered something that's different, they get to name it.
the charge will increase.
I think if I rewrote
I don't
all
fucking know
scientists,
that
He's like, shut up, it just does.
Yeah,
Trust
yeah,
it.
no.
Just trust it.
I don't know.
Okay.
They would call it like
Wait.
Jacob's system of nomenclature.
Yeah, it would make it so easy.
All right.
It's like Dr. Seuss.
Dr. Seuss.
Dr. Seuss does physics.
Better. So, a fully charged parallel capacitor plate remains connected to a battery, so what doesn't change? Voltage. Voltage stays the same. But capacitance, what happens to that? Go up or down? It increases. Capacitance goes up. and this stays the same, this has to increase for that to be an equality. All right, so it increases. We're gonna do this until you guys get these all right. There's a lot of these. We can keep going.
Remains connected to the battery. Yeah, I was like, yeah, you just gave it away.
How does the charge go if it's already fully charged? Like, how are you adding to it?
So it gives you more
I don't know, it makes sense.
Just shut up, it just happens, right?
Capacitance is the ratio of
That's what we're right on this example. Just put your answers up, right? It just works.
If you change the capacitance, now you can store the charge with the same voltage.
But did we do it again? I thought we just leave it hooked up and it was already fully charged.
Right, but we changed the capacitance.
Oh, I didn't know that.
Well, if you put a dielectric in, right, it increases the capacitance. All right. Oh God. All right. Okay, please discuss. We're gonna have to do another question, guys. Unless you get this right. They're talking.
It's
So this stays the same. This stays the same. And this increases. What did you guys put? Increases. She just fucking said it. Yeah. How did we fuck that up? Come on, guys.
I mean, you don't have to. But if you plan on like nailing the final.
Jokes on your head.
All right. Well, we got a little.
She just said it.
Okay.
Was I sleeping?
No. Oh. Okay. Well, it increases. Okay.
That was a hard thought.
What does the dielectric do to capacitance?
It
It increases it. Otherwise, we wouldn't bother with them. Okay. That's the whole point of dielectrics. All right. Let's turn it on.
Alright, this is awesome.
Oh my God.
Flash drive. For a second, but then it worked.
Higher. One who cried wolf. It's the same.
Okay. Okay. Try again.
But why though? I don't know, it just fucking does. Well, yeah, it's freaking electric field is equal to electric field not over K. If K is anything bigger than 1, it's got to decrease. Plus the fucking, all the insulators and shit, all this, you remember, it muffles it, dampens it, that's a word she used. Jives with it. Whatever, it's fucking.
Yeah. Okay. It can be an improper fraction. Thanks, smartass.
I'll be here all day.
What do you mean? That would suck if you were all day. For like 2 hours.
Oh wait, it's not Tuesday.
Right?
Oh yeah. All right.
Being a janitor. Maybe listen to reggae. Smoke a weed in there.
Oh no.
Nice.
Except that that's not right.
What?
Okay. So
What?
when it decreased, was it connected to a battery?
For fuck's sake.
Right? If it's connected to a battery, what stays the same? Voltage. How do we get the electric field in a capacitor? Right? Voltage is equal to electric field, which is constant, right? Times D. Did we change V?
No.
Did we change D? The electric field stays the same. What happens, and also electric field depends on right?
I'm lost.
So what did we not change? Charge. We did change charge, right?
Yeah, we did.
We changed charge. Okay? But remember, this now becomes okay? What happened to the charge? It went up by how much?
Okay. Or
Oh, I can't.
Okay? So electric field doesn't change.
These fucking battery problems.
So that means every single person in this room got it wrong.
Yes,
Yeah.
that is 100%.
But like you guys were really confident
Yeah.
with your wrong answer. You convinced the people that got the right answer to change their answer to the wrong answer. Which just proves that in life it's really more important to be convincing than to be right. So the electric field stays the same. So
Will we be done with this now?
electric field goes down when?
When it's not plugged into a battery.
When it's not connected to a battery. Okay? So that was the condition we were dealing with before. If you're plugged into a battery, electric field stays the same. All right? So the important thing is being able to reason through which things stay fixed and which things change. This one was a hard question. All right, so let's look through this question. We have a parallel plate which has this area defined by this. So this is our area, separated by a thickness. Thickness should correspond to D. And then paper with kappa of 3.7, that should be giving us our kappa or epsilon. And dielectric strength, last but not least, that's giving you your max E. So the first thing we want to find is capacitance. Here's our parallel plate capacitor. I'm just going to draw it from the side. So this has 2 centimeters. This is 3 centimeters. That's the area of our plates. They're separated by a distance of 1 millimeter. And in between them is paper. I'm going to represent paper with this, let's make it blue. Paper. So that's going to match our dielectric. I don't know why it's blue paper, but you get the idea. So that's our paper. It's got our dielectric constant kappa. So we just go to, for our parallel plate capacitor, we don't have to rederive capacitance. Capacitance is just going to be kappa epsilon naught. Now this can sometimes just be called epsilon times A divided by D. So this is pretty straightforward for part A. We're just going to plug and chug. So 3.7 times 8.85 times 10 to the negative 12th Coulomb squared over Newton meter squared. The area is 0.02 meters times 0.03 meters divided by D, which is 0.001 meters. When you plug all that stuff in, you get 20 times 10 to the negative 12 farads, or you can write this as 20 picofarads. So our capacitance is going to be 20 picofarads. All right. Part B takes a little bit more thought because we want to find out what the maximum charge is that can be placed on our capacitor before what happens? Well, Qmax before dielectric breakdown. We know dielectric breakdown happens at Emax, which is the dielectric strength of 16 times 10 to the 6th, that's mega volts per meter. So remember, that is our Emax. And this is what dielectric strength means. So we want to just figure out how much charge can be placed before we get E max. And to do that, we're going to first have to calculate delta V, because we want to use the definition of our definition of charge from our definition of capacitance, which is that C is equal to Q over delta V, which means that Q, in this case Q max, is going to be equal to C delta V. But we still don't know delta V, but we know for a capacitor, delta V is equal to E times D. And this is only for a parallel plate capacitor, but it's an equation we should know. So Q max is equal to C E D, and we've already figured out what our capacitance is, so that's 20 times 10 to the negative 12 farads. Our electric field is 16 times 10 to the 6th volts per meter, and D is, move this over, D is going to be 0.001 meters. You can see that we'll have some good cancellation here with units. Meters cancels meters. And then remember, farads are coulombs per volt. So the volts are going to cancel, and we'll just end up with coulombs, so that's good. And this is going to give us 0.32 times 10 to the negative 12th, not 12th, 10 to the negative 6 coulombs, or 3.2 times 10 to the negative 7, but this works too. So the reason we write it that way is that we can call it 0.32 microcoulombs. And that is our maximum charge. Which we can find here.